No, it's okay.
So we Latvian company SLICKER. We do a novel 3D display. It's complete new principle. And we're trying to make a 3D display for everyday use. And I explain in brief what it is. So, in our point of view, the 3D displays is a near future device, and that will replace all 2D media soon, as soon as possible. Because of human visual system is binocular and can only function normally in three-dimensional space. All other media is spoil the visual system and do first of all convergence accommodation conflict, because we constantly see the flat screen and our eyes constantly focus it in a flat surface. So the 3D media is in our near future, but there is some problems to implement and for the market and for the commercialization of the devices. We see two main drawbacks of the system is convergence accommodation conflict, is the first and main problem of this. And two problem is field of view, depth of field, and resolution trade-offs. These problems in combination makes difficult to implement these systems. So how we can improve this? I quickly explain what is convergence accommodation conflict. It means that all two-view media, including 3D cinema, all solutions that use stereoscopic effect. It is optical trick. It's in fact not 3D space that we see in real world. That's because actually the image always in the screen that users see in the device, and objects in real 3D space in different place, and our AI-axis focus on one object, and lens of the eyes focus in another place of the space. And this conflict causes headache and discomfort for the user, and it can be continuously used more than 20-30 minutes. 3D cinema works more or less well because the distance from the user to the screen is relatively large, and you can see the movie about 1.5 hours, but not more. And even in that case, most users feel discomfort. So we're trying to find simple and economical solution to improve this. Now I explain how we find the solution. The main problem for 3D displays is information capacity of the device. We need informational capacity to improve sufficiently, and here you can see on above examples of elementary images used in 3D displays. On the left, it is small pixel sampling, about 5, then 10, then pixel sampling, then 20, then 40, and 80. And you can see that the better resolution of elementary images, the better will be overall resolution of 3D image. And you can quickly calculate by the standard lens formula where the focusing plan will be. Central depth plan, it call it in integral imaging, and in one case in 10 millimeters, 20 millimeters, 40 millimeters, 80 and 160. So the better pixel sampling is, the higher quality of 3D image you will get. But there is a sufficient problem because all commercial screens has a relatively small resolution. Even on 4K display, you should have 2 millimeters pitch to achieve about 36 different angles of view. And in that case, if we have that type of lens, we have more or less normal depths of the 3D image. Typically, lenticular and parallax barrier should have small period to remain invisible, about 100 LPI. It's far below needed pitch of 2 millimeters. Moreover, parallax barrier is dark. Only a small fraction of light passes through slit, and it needs increasing of brightness of the display for several times. In the case of lenticular, stacks of the neighboring lens will be clearly visible. So we try to find alternative solution. Alternative optical layer to remove the faceting and improve 3D image integration. It is possible with 2 decentered microarrays, producing in combination an array of overlapping macro lenses, call it Gabor superlens or compound eye array. Now I show you our concept. On the left, you see typical lenticular with total track length relatively larger than our solution, and optical material waste is much larger. And our film solution, it is a film about from 50 to 200 microns, and it produces almost the same optical effect, but with several sufficient advantages. It is smaller detail, first of all, and that means larger information capacity with 4 factors the same and all other parameters the same. Another advantage is optical material economy, flat invisible structure for the viewer, and some perspective error correction because it's partially heliocentric system. It looks like this is just schematic, is not fully correct, but principally. On the left is lenticular, and the principal point of the lens is on the lens. And our solution, it is shifting perspective. When you see from the side, apertures of the lens is moving because it's partially heliocentric system. And this is flat. And how we improve informational capacity. There is a concept of, there is some solution invented by a Japanese inventor, Hideaki Kakeya, and we improve it with our system. He used relatively larger lenses to improve information capacity of elementary images. The larger the elementary image is, the better resolution you can achieve. as you can see in the image on the right. In first case, we have CDP 80 millimeters, and the second in 2 times larger with all other parameters the same. Resolution is twice larger, but we can just use lenticular with larger SAC because lens will clearly visible for the viewer, and material waste will be larger, and stacks between other lens will be clearly visible. And in our case, it's not so, because it is microstructure and the user cannot see separate micro lenses. Each micro lens is about 25 microns. Now I show you what we achieve. We had developed prototypes. It's not very good from first time because it's some intolerance in while printing and so on, and aspherics was not very good for first time, but I can show how it look like from the first trial. Here you can see film applied on the plastic, 200 microns film, and you can see 3D image on commercial screen. Even with drawbacks, it is close to commercial lenticular by its quality. Here is just a photo of the screen. And also we developed a light field panel. You can see some drawbacks caused by field curvature. That's fulfilled because of improper aspherics and some intolerance in while printing. But anyway, it's a very impressive image. In reality, it's deep, and it feels not like a lenticular image. Then we return to optimization and try to optimize our system. Here you can see aberrated wavefront. This is typical for the system. Center is good, but side of the lenses is aberrated. And then we tried to improve. We tried to use high refractive index material with a starting in modern times more or less common, starting from 1.7 refractive index. And we experimentally tried another aspherization of the lenses, and aspherics is quite important for our system, because with aspherization you can improve Pascal field, and we achieved that. As you can see, the peaks is very narrow. This is a side view of 2 millimeters SAC, 2 millimeters pitch. It means that every elemental image will be 2 millimeters in wide. This is a center of image, and this is a side of the image. And our system now can resolve about 36 angles. It is more or less super multiview display condition, because when you have 36 angles, you can improve sufficiently Convergence accommodation conflict, because the user can see image out of the screen. His eye is not focusing on the screen anymore. This is optimization of the image with better aspherics and with high refractive materials. This is UV curable resins and with a high refractive index, and we improve aspherics, and you can see the image how it looks on the detectors on ZMAX. This is a detectors. Image is in space, and our system focuses 3D image in space. This is the quality of the image, how it simulated in ZMAX. And this is focus on real 4K screen, just simulation, but in our view, it will be something like that. This is ideal case, how it should be to resolve 36 point of views or 36 views to improve convergence accommodation. And this is a real focusing, side, center, and another side. It is again 2 millimeters integral imaging, 2 millimeters elementary imaging for integral image display. And system parameters we expect: viewing angle main zone 28 degrees, views about 36, but with ghosting of 50%. But if we add to the system some parallax shift, then there will be no ghosting. And resolution we expect about 960 and 720 respectively. And then after that, we're trying to improve other drawbacks of the system is viewing angles using Polarizer. It is common methodics to improve, but in our case is something another solution, because principal points of the super lenses is not in plane of the screen, it is higher. And we use it partially collimated backlight with angle of emission about 30 degrees. And we can improve viewing angles twice. And you can see image. Actually, it is a half of the image because the black zones are polarizers. In reality, there will not be such dark. It is twicely dark than in reality. But you can see in one step. Actually, you can see only one lens. There will be another with another polarizer. And you can see 25 degree one side, 0, and 25 degree other side. So complete viewing zone will be almost 50 degree, almost. It is very good for 3D displays, and it is more advanced implementation. So this is the simplest implementation of our system, and this one is more advanced. And this is production line we planned. This is a wide web roll-to-roll printer. This is a dispenser unit, coating unit, blade, preheat unit to remove solvent from UV curable resins. This is a printed roller, diamond and gravity metal roller. Lens height will be about 25 microns, and this is ready film. We print the lens from both sides of the film with well-lit coating. So this is our team. This is our scientific team. They will help us with optics and with materials. And there is our founders, Andrei Pilkins, it's me and Yuri. We are inventors of this. So basically, it's all. If you have some questions, thank you for the watching. Thank you very much.
So if no one has questions, I would like to ask one question about those lenses in lens array. Do I understand correctly that you have lens array with long cylindrical lenses?
Yes.
So first imagination is that, okay, if we have some plain lens, we have to have matrix, not array. But there is something probably why you can use array, not lens matrix.
The arrays is here. This is one array, is very small micro lenses. And this is another array of very small micro lenses. This is a flat film, but together they produce micro array, relatively micro array, because it's just 2 millimeters. And it replaces lenticular, because lenticular is much larger. And it can be produced with much larger waste of optical material. And overall, total track length of lenticular is larger because of you should add here the height of the lenticular lens. Our solution is just flatter, and optical path is smaller. Therefore, our display will be more compact, and it's more friendly to another film like touch screen or something like that. And also, if another matrix, transparent, for example, matrix, placed directly after the film, and we use it for 2D, 3D, 2D transition, it is not refract. Lenticular will be refract light even if even the lens applied directly on the screen. But if our lens applied directly on the screen without some distance, it's not refract light. So it's just more compact solution, and optically it will be a little better because we have two objectives, not one lens, one objective, but two, and some we can correct some aberration also.
Okay, thank you. Someone else wants to say something or have some question? If not,
if no questions, I would like to tell a few words.
Okay, please.
Yeah. Dear colleagues, you had seen the presentation, which could be called and is called in European Union terminology as disruptive innovation. The company is offering something which is not on the market, or if suddenly something in the market, this offer is radically better. The company succeeded to get Seal of Excellence in the competition for Horizon 2020 SMS project second stage now. That means they were very close to winning the financing, successful winning financing about 5%. They get mark something like 13 points from 15. to get winning a little bit more you need it. But anyway, seal of excellence means that two commissioners of European Union are advising investors to invest in this invention without any doubt, because invention is tested by absolutely independent, very professional evaluators around in commission, not locally. We have only a few such cases in Latvia. We have succeeded with one company winning this such money. It's a Nobel Prize size, Hansa Matrix, but this company also is very close to the success. Hopefully this next framework program, Horizon Europe, they could be more successful to go ahead with new applications allowed to apply once more with better explanation as well as maybe improved prototype. And we have in our club of so-called advanced SMEs several such companies with success in Europe and this competition for SMEs. And before Baltic Scientific Instruments succeeded to be among the first winners on first stage application. Thank you.
Thank you.
Thank you.
Thank you very